Let me, didn't turn on the recording, but that's okay. All right. So we get that many atmospheres. So what did we have to do here? It's not enough to just have the equation. You have to go through and make sure everything is in the right sort of numbers. And I'm going to tell you, you're not going to ever see a problem where you have the pressure automatically in atmospheres, you have the volume automatically in liters, you have the temperature automatically in Kelvin. You're going to have to convert one or more of them into the proper units. You're going to have to. I can guarantee you, no problem will you ever see where the temperature's in Kelvin. It's always going to be in degrees Celsius or Fahrenheit. If it's in Fahrenheit, what do? You got to convert it to Celsius, and then you've got to convert it from Celsius into Kelvin. So you'd have to take what is it, 5/9 of the Fahrenheit minus 32. Right? Take the Fahrenheit minus 32, divide and multiply times 5/9. You get, and then you're going to have to add 273.15 to it. And so to get used to the idea that no matter what you do, you're going to have to convert it. All right. No matter what you do. All right. So let's do another one. We'll do another one. All right. And really, when you get used to the whole idea, it's all plug and chug at the end of the day. I think gas laws are actually one of the easier chapters. Some people find it hard because there's a little bit of math involved, but I think gas laws are actually fairly straightforward. Once you get the joke, you know that you got to have the right units. Once you have the right units, it's plug and chug. That's what it is. It's just plug and chug. And so we might have something that looks like this. What is the temperature of a sample of nitrogen gas? Let me make sure that the meeting is accessible. It says lock meeting, so we're good. What's the temperature of a sample of gas that is in a 8.00 liter container at, let's say 4.184 atmospheres? Nitrogen gas. Let's see, what's the temperature sample of that? And let's say it's 4.200 grams. Let's see, we got pressure. Where's the pressure? Got the pressure, got the volume, we had the amount, and I just want to know the temperature. Okay. Okay, so I look at this and I see no pairs. Not just because we're doing the ideal gas law right now, but this is a question you have to ask yourself every time. Do I see pairs or not? And I don't see any pairs. I see individual units. Okay, so I know it's PV equals nRT. And I'm looking for the temperature. So I'm going to go ahead and solve this. So I say temperature is pressure, volume, nR. Okay, so I just solved for temperature. That's all I did. All right, hopefully I did that right. Did I do it right? Let's see. Temperature PV over, yeah, I did that right, didn't I? All right, well, that's good. Okay, be more confident. Don't look quite so confused. All right, it's just all I did was a little bit of rearranging. Okay, so what else do we have going on here? Well, first off, and I didn't specify, but I want the temperature in degrees Celsius because I don't have a thermometer that reads in Kelvin. My thermometer is reading degrees Celsius or Fahrenheit. So I want my temperature in degrees Celsius. Okay. What else do we have here? Oh, wait a minute. That's nitrogen gas, and I'm told we have so many grams. What's nitrogen gas? You should know that nitrogen gas is one of our diatomics. And it's not N, it's N2. And so the molar mass of nitrogen gas is not 14, it's 28.0 for the molar mass of nitrogen gas. So it's 28.0 grams into for every mole into. See how this stuff just never goes away? It just never goes away. It's chapter 2, chapter 3, chapter 4. That's the beauty of chemistry. It's not like, it's a real science. It's not like sociology or psychology or something like that. This is a real science. Things don't change depending on your opinion. Okay, there's no opinion here. And it's still nitrogen gas is still an N2. And so I think I'm going to have to at least find the moles. As I can guarantee you, regardless of whatever formula you have up top, you're going to have to find the moles because you never use grams in anything. Okay, so 4.200, let's see, how many moles is that? 0.15 mole N2. Okay. And so what do we need here? I need an R. I got to find my R because I know I need the R, right? What R am I going to use? I look in the back of my textbook and I look for the one that says atmospheres. Yeah, that's the unit that we're using. So it's 0.0821 liters atmospheres moles Kelvin. All right, remember, this is a pro tip, right? How do you pick your R? You pick your R based on the units. That's how you pick your R. And so now what? Well, let's see. I got the pressure, no problem there. I got the volume, that's 8.00 liters. I just found the moles, and I have my R, so I'm all set. Remember what I said? You use your R, use your formula as a checklist. This is how you solve these problems. And so we say, well, you know what? The temperature in Kelvin, because look what your R says. So your R says Kelvin. Don't ever lose sight of what it is that you're calculating. You're going to get your answer in Kelvin. What do I want? I want degrees Celsius because there's an extra step involved here. And so we say temperature is what? The pressure is 4.184 atmospheres. We got the volume. What is the volume? 8.00 liters. I got my N. What's my N? That is 0.150 mole. And I have my R, which is 0.0821 liters, atmospheres, moles, Kelvin. And oh, by the way, you will do this too. Eventually, you just stop leaving on those units for the R. Because if you pick the R, you know it's right, right? I'm just saying, we all do this. We end up leaving off the units with gas law calculations a lot of times, okay? Just because it's just more convenient. Not that it's right, it's just more convenient. So we go 4.184 atmospheres, right? Times 8 divided by parentheses 0.15 times 0.0821, close parentheses, and I get 20. Wow, it's a pretty hot temperature there. Let's see, really? 2,717, is that right? Let's see, 34. Yeah, I guess that is right. Yeah, don't ever second guess yourself on these problems. 2718, that's in Kelvin. All right, that's in Kelvin, which means we need to do what? We need to subtract off 273 to get to degrees Celsius. So I'm going to say minus 273. And I get 2445. And that's degrees Celsius. And let's not forget, what's our sig figs? We've got 3SF here, right? You got 3SF. So our answer should be 3SF. So we go 1, 2, 3, look one more over, and we get 2450 degrees Celsius with the correct number of sig figs. Like I said, when you hit physics, the physics folks will say, you guys really know your sig figs if you don't know anything else. So I'm pretty sure I got that right. 4.184 times 8 divided by 0.15 times 0.08. Yeah, that's right. Okay. Pretty hot temperature. There's a lot of stuff in there. Okay. But that's the way it works, You have a small container with a lot of stuff in it, it's going to be hot if it's going to have that kind of pressure going on. All right. So that's how you do that. Okay? With so what do we have so far? We have of course kinetic molecular theory. And if we were to say, a short definition, that would be what? Small, fast, and far apart. Far apart, not just a little bit apart, but far apart. Small, fast, and far apart. And we have P1 V1 over T1 equals P2 V2 over T2. And we use this when we have pairs. And we have PV equals nRT, and we use that when we have no pairs. Right? PV equals nRT. Ideal gas law we use when we have no pairs, and we pick our R based on what? The units. Okay, now this is called the ideal gas law. So what's the difference between real gases? Ideal is not real. It's like people. There's an ideal person. There is no ideal person. You got real people. Well, same thing with gases. We have ideal gases, and they behave according to PV equals nRT. But what do the real gases do? Well, real gases, as opposed to KMT gases, have volumes. So they have volumes, which means the pressure is higher for real gases because they actually have a volume. Makes sense, right? If you have a point versus a volume versus something that actually has a volume, which one's going to have the higher pressure? It's going to be the thing that has actual volumes because you're trying to squeeze stuff into a container. So real gases have a pressure that's higher than ideal. How about real gases also have a pressure that's lower because they have attractions. Okay, so there's competing processes going here. Real gases have volume, so the pressure is higher. Real gases interact with each other, so they're closer together than they would be otherwise, so the pressure is lower for real gases. Now, if this is the case, why in the world do we have PV equals nRT, right? If that's not the case. This actually works very well. It works well. It works well at low pressure and high temperatures. Low pressures and high temperatures, ideal gas law works really well. It turns out that the air that you're breathing is technically low pressure. It may not make sense in that sense, but if you look at the pressure of gas, say on Saturn, many times more pressure than what we have here. Okay, our gas that we're breathing is technically low pressure, and the temperature of the gas that we're breathing, air, is actually considered high temperature. The average temperature of the universe is right around, I think, 4 Kelvin. The actual average temperature of the universe is actually quite cold. The universe is quite cold. Our temperature here at around 298 Kelvin or 300 Kelvin for today, because it's going to get pretty hot, is actually considered pretty high temperature. The average temperature of the universe is much colder than what we experience here. So this Ideal gas law actually works really well for ordinary temperatures and ordinary pressures that we experience on a day-to-day basis. It works really well. If you get really cold or you get really high pressures, then you have to break out something called the van der Waals equation. I think I spelled it right. I may not. Van der Waals, okay? Um, this equation you'll see in the textbook has all these correction terms in it. It's got an A term, it's got a B term. One term is correcting for pressure, the other one's correcting, one term's correcting for actual volumes of the molecules, and the other term is actually correcting for attractions. It's a correction, all right? And it's an ugly equation. No one ever uses it. All right, it's in the textbook. It's there. You should look at it. You should give it a look. The van der Waals equation, just to realize that you can take any equation, and this is the thing that I learned when I was in your position. You can take any equation and make it do whatever you want it to do if you add enough correction terms. So that's what the van der Waals equation is all about. It's actually taking the ideal gas law and you're adding correction terms to it. So in that sense, it's a silly equation. It really is. It's just like, why? Well, and you can make your whole PhD on coming up with correction terms, and that's what you do. All right. So don't worry about it. Okay. Just know that it exists. It is in your textbook. That if you ever become an astrophysicist and you have to, worry about things like the pressure of methane gas on Neptune, maybe you'll pull out that equation. Something tells me you still won't pull out that equation, the van der Waals equation. You'll pull out something else. All right. So just be aware that it exists. Okay. So this is a good stopping point. So what I'm going to do is I'm going to go ahead and stop.